get the phone over this motherfucker. Stay long, stay long. With so much drama in the LPC, it's kinda hard being Snoop D or Double G, but I somehow, some way, keep coming up with funky ass shit like every single day. May I kick a little something for the G's and make a few kids as I breeze through. 2 in the morning and I'm still jumping cause my mama ain't home. I got bitches in the living room getting it on and they ain't leaving till 6 in the morning. So what you gonna do? Shit, I got a pocket full of brothers and my homeboys do too. So turn off the lights and close the door. But for what? We don't love hoes. Yeah. So we gon' smoke an ounce to that. G's up, hoes down. Why you motherfuckers bounce to that? Rolling down the street, so get down. Sipping on good. Laid back. With my mind on my money and my money on my mind. Rolling down the street, so get down. Sipping on good. Laid back. With my mind on my money and my money on my mind. I got me some shit with gin. Everybody got their cups, but they ain't chipped in. Now this type of shit happens all the time. You gotta get yours before I gotta get mine. Everything is fine when you listen to the D.O.G. I got the cultivating music that be captivating me. Who listens to the words that I speak as I take me that way to the middle of the street and get to lagging to this bitch named Shady. She used to be the homeboy's lady. 80 degrees when I tell her please raise up all these NUTs cause you get none of these at ease. As I pop up the dog pound filled with breeze, the ice up jet. Rolling down the street, so get in now. Sipping on good. Laid back. With my mind on my money and my money on my mind. Rolling down the street, so get in now. Sipping on good. Laid back. With my mind on my money and my money on my mind. Later on that day, some bubonic chronic that made me shook shit. This ain't no joke. I had to back up off, but baby sit my cup down. Tangeray and chronic, yeah, I'm fucked up now. But it ain't no stopping. I'm still popping. Dre got some bitches from the city of Compton to serve me. Not with a cherry on top. Cause when I bust my nut, I'm raising the vodka cop. Don't get upset, girl. That's just how it goes. I don't love you hoes. I'm out the dump. And I'll be rolling down the street. So get in now. Sipping on good. Laid back. With my mind on my money and my money on my mind. Rolling down the street, so get in now. Sipping on good. Laid back. With my mind on my money and my money on my mind. Rolling down the street, so get in now. Sipping on good. With my mind on my money and my money on my mind. Rolling down the street, so get in now. Sipping on good. With my mind on my money and my money on my mind.
How are we doing? I was starting to wonder if the chat was working there. Questions while we wait for others to come in? No, nothing? We're all good? How are we doing with well, it's a good idea to take one of those two courses. You probably should not be doing both. The fact that they're online makes it easier, but I mean, if it was in person, I would tell you just do one. I'm going to let you decide what you want to do since they're online. I mean, they are relatively straightforward math courses. There's no reason for you not to get an A in any of these. But 2 simultaneously is a lot of work. Yeah. Yeah, I mean, a lot of people have to do them. They are core courses for engineering. And they're great courses. Gin and Juice by Snoop. All right, let's get started. Questions before we do so? There's not much overlap. 263 does assume some 262 knowledge. So that's one thing to keep in mind. Not much, but it's best that, I mean, especially if it was in person, it's much better that you do 262 first and then 263. Now, being online, again, I'm going to let you decide. All right, let's get started. We saw, what did we see? We saw the integral test last time. Yeah, I am teaching Math 180 in the fall, for sure. Is the schedule out yet? Do we know what time these courses are being taught at? So last time we did the integral test, and an immediate consequence of that was the P-series test. It is out, thank you. And I am teaching 222 in the summer as well. Yep. So we saw the P-series test, which says that 1 over n to the P converges if P is bigger than 1 and diverges otherwise. Now consider this. Suppose we have this series, which is almost a P-series, right? Correct. The P-series test, right, this gives you convergence, but it doesn't tell you what it converges to. And as we suggested last time, most of these questions are open questions, right? Unless P is even. If P is even, we know what the series converges to. If P is pretty much anything else, we don't know what it converges to. Arun, a very nice observation here. Kind of looks like the arctan, so you might want to apply an integral test. Very nice, very nice. After showing that it's positive, continuous, and decreasing, which I think is pretty clear that it will be. But I wanted to make a relationship between that and a P-series, right? I mean, if the +1 wasn't there, then you would have a p-series. Have you taken a crack at any of the millennium problems? I mean, I think everybody has. At least just for fun. But if you take Math 180, I'll show you one question that we're working on. Not from the millennium problems, but something else. Well, exactly, right? So the point is, right, if the plus one wasn't there, this would be a p-series. So this behaves kind of like a p-series. And you've noticed that because the denominator is bigger, right, 1 over n squared plus 1 is actually less than or equal to 1 over n squared. And you have this one here. This one here is a convergent p-series. So now we are sort of in a comparison test situation, right? Remember, with integrals, if you have one function less than or equal to the other, positive of course, then the integral will be the same as well. So if you have an improper integral here from a to infinity, if the bigger one converges, then the smaller one converges. And conversely, if the smaller one diverges, then the bigger one diverges. We have the same situation here. We have a comparison test for series. Suppose you have some sequences which are related by this inequality. Then, if you add the terms, the series are related by this inequality as well, right? I mean, we're just adding the terms. So the inequalities are maintained throughout, and we're good to go. So following this inequality, we see that if the larger one converges, right, if the larger one is less than infinity, then the smaller one is less than infinity. So if the bigger one converges, then the smaller one converges as well. Conversely, if the smaller one diverges, then the larger one is bigger than or equal to infinity. So the bigger one has to be infinity as well. And that's the proof. That's the proof of the following statement. If the bigger one converges, then the smaller one converges. And conversely, if the smaller one diverges, then the larger one diverges as well. And here, if we can prove this inequality, which is trivial, right, because the denominator is bigger here, so a bigger denominator makes a whole fraction smaller, but, I mean, if you want to prove this in complete detail without making that argument, notice that 0 is less than or equal to 1. So if you add n squared to both sides, we get n squared is less than or equal to n squared plus 1. And then multiply the whole thing by 1 over n squared times n squared plus 1, which you know is equivalent to cross multiplication. And this gives us 1 over n squared plus 1 less than or equal to 1 over n squared. This, of course, being positive, we are now in exactly this situation. Since this converges by the p-series test, where p is equal to 2 bigger than 1, the smaller one converges by comparison. How are we doing? Let's take another example. Ln n over n squared. You see the issue with the comparison test, right? With the comparison test, you have to establish some inequality. And not just any inequality. An inequality where either something bigger converges or something smaller diverges. So you need some sort of idea of what you're working towards. Are we trying to establish convergence or are we trying to establish divergence? You need an idea of what's happening. And here, what's the idea? Well, you know that ln n goes to infinity. I was trying to establish this inequality. This is the inequality we were working towards. So we started with 0 less than or equal to 1. You know that to be true. We added n squared to both sides, so the inequality is maintained. And then I multiplied by this positive quantity. Mohammed, how are you doing? And then we multiplied by this positive quantity so that the inequality is maintained as well. Having done that, we get the required inequality. Moving on to this, right? I mean, what I was suggesting is ln n goes to infinity, but this goes to infinity as well. And Haroon is suggesting that ln n is less than n. And you're absolutely right. You can prove that. Ln n is less than or equal to n. So if you multiply the whole inequality by 1 over n squared, what do we get? We get ln n over n squared less than or equal to n over n squared. This is, of course, bigger than or equal to 0. And this is 1 over n. And conclusion? What do we know about this series? The series 1 over n diverges by the p test, where p is equal to 1, less than or equal to 1. So now we have the bigger series diverging, which doesn't tell us anything about the smaller one, right? If the bigger one is infinity, if this is equal to infinity, this is less than or equal to infinity. It could be equal to infinity. It could be less than infinity. No conclusion here. No conclusion. So a valid effort, but it doesn't tell us anything. And what happened here? What happened is that we chose the wrong series to compare it to. We chose something that was way too big. Integral test, perhaps, but let's do it with, let's go back to this. Why is p equal to 2 bigger than 1? In the previous example, well, that's what the p-series test, I've rubbed it off now, but it was stated up there. Well, if you make it even bigger, then that's even worse, right? I'm suggesting that this n was chosen too large. It was chosen too large, right? You know that ln n goes to infinity, but it actually goes to infinity slower than any positive power of n. So instead of choosing n to the 1, I claim that we can choose n to the 1/2. And we're going to prove this momentarily. Exactly. Thank you, Paul. Paul has answered the question where the 2 was from. We were looking at the series 1 over n squared. So it's a p series where p is equal to 2. Right, so let's prove it. Here's the claim. For n large enough, or for x large enough, ln of x is less than or equal to root x. Let's prove that. Let's prove that by looking at the limit of ln x over root x. What is that limit? This has the form infinity over infinity. So we can do a L'Hopital rule. 1 over x over 1 over 2 root x, which is, if you flip that, that's 2 root x over x, or 2 over root x, whose limit is easily seen to be 0. Well, yes, for x large enough is good enough, right? And we'll argue that in a moment. Because, as you know, with series, it's just the tail end of the series that matters, right? When you're doing the integral test, your function doesn't have to be, or doesn't have to satisfy the hypotheses in the beginning. It's just eventually, right? Because you're adding infinitely many numbers. So the finite first few don't matter. Even if it's the first 10 million terms, it doesn't matter. Because what's important is 10 million 1 to infinity. If you add the first 10 million terms, it's going to be a finite number, regardless of how big it is. So here, the limit is 0. What does that mean? What does that mean? That means that this function, for large values of x, this function is close to 0. So for large x, this function is close to 0. So it's going to be less than 1. Right? You can make it as close to 0 as you want. So it's going to be less than 1. And consequently, for large x, ln x is less than root x. You can make it less than or equal to, it doesn't matter. Yeah, that's fine. You can make it more precise. Absolutely. So for large x, in other words, x larger than or equal to k, and so we have this for large values. In other words, for n larger than or equal to k, we have ln n less than or equal to root n. And now, if you multiply this whole thing by 1 over n squared, you get ln of n over n squared less than or equal to 1 over n to the 3 over 2. This, of course, being bigger than or equal to 0. And now you have a convergent P-series. Where P is 3 over 2, which is bigger than 1. So by comparison, by the comparison test, the smaller one converges as well. We don't know what it converges to. We just know that it converges. Actually, whatever it converges to is going to have to be smaller than whatever this converges to. And by that I mean the sum starting at k. How are we doing here? Questions? Anyone? We're good? Well, I mean, you see the issue with the comparison test, right? You have to establish some sort of inequality. And that's always a lot of work. Surely, there must be an easier way. There is. And don't call me Shirley. How are we able to make the claim that ln x is less than root x? I'm suggesting that ln x goes to infinity slower than any positive power of x. And you can prove it in exactly the same way we did. Take any positive power of x, look at ln x divided by that positive power of x, and take the limit as x goes to infinity. You have infinity over infinity. A quick L'Hopital's rule gives you the answer in exactly the same way. So that's how you can prove that. And now that you know, you're going to keep that in mind from now on. Well, why did we choose root x and not something else? An excellent question. We chose root x because root n divided by n squared gave us a convergent p-series. So any power of x less than 1 would have done the trick. I chose x to the 1/2 for convenience, but it could have been any power less than 1, and it would have been fine. Bigger than 0, of course. You would have gotten a different p-series, but the conclusion would have been the same. So the issue with the comparison test is that you have to establish some sort of inequality, and that's always difficult. There's an easier test known as the limit comparison test. And what does that say? Suppose you've got two sequences. Governed by the following inequality. And let the limit as n goes to infinity of 1 divided. Sorry. It's not an inequality. It's just positive sequences. And let limit as n goes to infinity of 1 divided by another be some limit L. So suppose the limit L exists. If L is bigger than 0 and less than infinity, then both series converge or both diverge. In other words, both behave the same way. Let's look at the proof. Proof is nice and simple. It's really just one line. And it'll explain why this is true. What does it mean for the limit to exist in BL? It means that for n large enough, this thing is very close to L. Or if you bring the B to the other side, you have AN is approximately L times BN. So the series AN is going to be approximately L times the series BN, but here you can take the L out, and there you go. So these two series behave in essentially the same way. So if one of them is finite, the other is going to be finite. And if one of them is infinity, the other is going to be infinity. Right? The L here, since L is not zero and not infinity, it really doesn't make a difference. Let's take a few examples. Questions before we do some? But if the series are to converge, it needs to approach zero. What needs to approach zero, though? Right? If the series AN converges, then what approaches zero? Then the ANs themselves go to zero, right? AN, thank you, absolutely. Right. So, but what we're saying here is that both the ANs and the BNs approach zero essentially at the same rate. Right? Essentially at the same rate. So that, exactly that, common ratio. So if they're going to zero at essentially the same rate, then the series themselves should behave the same way. That's what the limit comparison test is suggesting. Let's take a few examples. We're asked to establish the convergence or divergence of the following series. Consider this. What's the idea here? Well, for large values of n, root n is the dominating term in the denominator. Right? This minus 1 is negligible compared to root n. So this series is going to behave like the series 1 over root n. So we're going to do a limit comparison. With the series 1 over root n. Now, what do you know about the series 1 over root n? Right? You know some things about this series. This series is a divergent p-series where p is 1/2, which is less than or equal to 1. Thank you, Sophia. It is a p-series, a divergent p-series. Is it though? Arun is suggesting that this series is smaller than that. Maybe it is. Indeed it is, right? I mean, if you cross multiply, you get root n minus 1 less than or equal to root n. And so minus 1 less than or equal to 0. Very nice. Very nice, right? So you could work backwards all the way to there. Very nice. But again, establishing an inequality, right, is always a bit harder. And what if this had been a plus 1? If it had been a plus 1, then it would have been harder. Absolutely. So we'll see that it diverges. If he's asking how do we know what to compare it to? Well, I mean, my claim here was that for large values of n, this negative one is negligible, right? Root n is the dominant term in the denominator. The numerator is constant, it's just 1, so forget about that for a moment. In other words, this negative 1 doesn't make a difference. So this term here for large values of n will resemble very much 1 over root n. So we're going to do a limit comparison with these two things. Here, Arun has suggested a straight up comparison, which works very nicely. So that works as well. But after this question, we'll redo it with a plus, and you'll see that with a plus, it's harder to establish an inequality. You might want to try that, Arun, while we're finishing up the limit comparison. So let's do a limit comparison. What do? It's 1 divided by the other. It doesn't matter which one. 1 divided by the other. Let's evaluate this limit. You're dividing by something. Let's multiply by the reciprocal. And we get root n over root n minus 1. Let's factor out a root n from the denominator. And now the root n's cancel, and as n goes to infinity, 1 over root n goes to 0. So this limit is 1. 1 is bigger than 0 and less than infinity. So both converge or both diverge. This one diverges, and consequently, this one diverges as well. So that series diverges by the limit comparison test. How are we doing? Right, the beauty of the limit comparison test is that you don't need to establish this inequality. And you know, I mean, it was relatively easy to do so in this situation. But what if you had a plus 1 instead? If it's plus 1, right? I mean, the indexing, the numbering here, whether it starts at 1 or 0, in fact, in this case, or 2, really has no bearing on convergence. it's going to affect what the series converges to. But here, first of all, in this case, it diverges, so there's no point in there. But in general, these tests give you convergence or divergence. They don't tell you what it converges to. So it doesn't matter. Doesn't really matter. As long as you don't start, right? I mean, we had the minus here. So you didn't want to start at 1 because you'd have a 0 in the denominator. So that's the only thing you want to be wary of. You don't want to start at a place where you get a 0 in the denominator. So anywhere else, you're good to go. But here, it's not an issue. If it's plus, you could even start at 0, and we're good to go. What I want to bring your attention to is that, first of all, again, the plus 1 is not going to make a difference. So you could do a limit comparison test with 1 over root n, and the only difference is this would be a plus, plus, plus. The limit is the same. So you'd get divergence by the limit comparison test. Effie has answered her own question. Very good. So you see then a limit comparison test is going to be the same thing here. But let's try it Haroon's way by trying to establish an inequality. And you see the issue, right? I mean, you have 1 over root n plus 1. Here the denominator is bigger, so the whole fraction is smaller, and we're in trouble. Right? Because when you cross multiply, you get root n less than or equal to root n plus 1, or 0 less than or equal to 1. Right? So you could go here and move your way back up to establish this inequality. But it's going the wrong way. This is a divergent p-series. So if the bigger one diverges, you cannot conclude anything about the smaller one. The question arises naturally, can we do a comparison test with this? Indeed you can. And this will illustrate the difficulty in establishing the inequality. If n is bigger than or equal to 4, then root n over 2 is going to be bigger than or equal to 1. Right? Because if n is bigger than or equal to 4, take square root of both sides. And you get 2 less than or equal to root n. And bring the 2 to the other side by multiplying by 1/2. There you go. So you have this. So if you add root n to both sides, you get 1 plus root n is less than or equal to root n over 2 plus root n, which is 3 root n over 2. So in other words, 1 plus root n is less than or equal to 3 over 2 root n. And now cross multiply. which is again equivalent to multiplying by 1 over that. And what do we get? We get 2 over 3 times 1 over root n is less than or equal to 1 over root n plus 1. And now you see that the series on the left is a divergent p-series. So the smaller one diverges, the larger one will diverge as well. How are we doing here? So this example illustrates nicely why, if you can, you want to try to stay away from the comparison test. Limit comparison test, much easier because you don't have to establish an inequality. Case in point, consider this. Well, again, for large values of n, this minus 1 in the numerator and this plus 1 in the denominator are negligible, right? N is the dominant term in the numerator, and n cubed is the dominant term in the denominator for large values of n. So this is going to behave like n over n cubed or 1 over n squared. We're going to do a limit comparison with the series 1 over n squared. What do you know about this series? You know it's a convergent p-series. Where p is equal to 2 bigger than 1. So let's do a limit comparison. 1 divided by the other. Doesn't matter which one. As n goes to infinity, numerator goes to infinity, denominator goes to infinity. Let's factor out an n cubed from the top. And factor out an n from here. And then n squared times n is n cubed, which cancels with this one. As n goes to infinity, this goes to 0, that goes to 0, leaving you with a 1 over 1, which is 1. Exactly that, Arun, thank you. Limit is 1. Conclusion, both converge or both diverge. Right? 1 is between 0 and infinity. So both converge or both diverge. But This one converges. So the other one. Converges by comparison, by limit comparison test. How are you doing? Everybody comfortable with this? Let's do a few more. Do we always just use 1 over n squared because we know it converges? No, no, no. You have to adapt. It depends on the question. Here we used 1 over n squared because this term was negligible and this one was as well. So the series looked like n over n cubed or 1 over n squared. So it's very dependent on the series we were looking at. Why do we not have to change n to x to take the limit like before? I wasn't using L'Hopital's rule here. So since I'm not differentiating, I don't have to be working with x's. All I did was factor out an n from one of the terms. So you can do that whether it's n or x. If you wanted, because you were in an infinity over infinity situation, if you wanted to use L'Hopital's rule, everything should be in terms of x. So, I mean, back to Sophie, you can use the limit comparison test with anything. With anything. That's the answer. With anything, as long as you know the behavior of the other thing. Very nice. Very nice. Here you have observed that this term does not go to 0. So now let's change to x, right? Limit as x goes to infinity of 6 to the x over 5 to the x minus 1. This has the form infinity over infinity. And if you do a quick L'Hopital's rule, this is 6 to the x ln 6 over 5 to the x ln 5. And if you rewrite this in this way, we saw, right, first of all, the only thing that depends on x is this, and we saw when we were dealing with sequences that if that a to the x, if a is bigger than 1, this goes to infinity. So this is infinity and we're done. Diverges by the divergence test. Very nice observation. The limit is not 0, no hope of convergence. You could you could have done a limit comparison. Again, for large values of n, this -1 is negligible. So this looks like a 6 to the n over 5 to the n, or 6 over 5 to the n, which is a divergent geometric series. Where 6 over 5 in absolute value is bigger than or equal to 1. Yeah. So 2 ways to do it. Both give you the same answer. Haroon is suggesting yet a third way. Since the numerator is bigger than the denominator, at least eventually, then we're in trouble. Yeah. Yeah. Very nice. Very nice. So three different approaches all give you the same conclusion. That's always very nice. You tell me, Sarah, where do these come from? Right, what are we doing here? We have infinity over infinity. I changed to x's for obvious reasons. I was planning on doing L'Hopital's rule. So derivative of the top, derivative of 6 to the x is 6 to the x ln 6. Derivative of 5 to the x, 5 to the x ln 5. Thank you, Jean-Chan, coming from the L'Hopital's rule. How are we doing here? Questions? Without doing too much work here, if you're looking at this and you're thinking to yourself, I'm going to take some sort of limit. First of all, don't let the k fool you, right? Whether it's k or whether it's n, it's the same thing. It's just a dummy variable. If you want to rewrite this in terms of n instead, please feel free to do so. But imagine taking a limit, right? I mean, if you do a limit comparison test or anything, you're going to be doing a limit, and you're going to have a limit of sine k or sine squared k. And that's going to be an issue because you know that limit does not exist. Sine k is an issue because the limit as k goes to infinity does not exist. So I think it's probably going to be best to get rid of it. Let's start by getting rid of sine squared. And what do you know? You know that sine is always between -1 and 1. So sine squared can we establish an inequality for sine squared? Sine squared is always between 1 and one end. You tell me. It's tempting to say 1 and 1. Thank you, Haroon and Severa and everybody else. Thank you. Right? I mean, it's something squared, so it's bigger than or equal to 0, but less than or equal to 1. And now, if you multiply the whole thing by k over 1 plus k cubed, you get the required thing in the middle. So you see, Sophia's asking a good question, which a lot of people have. Right? If you're squaring both sides, why isn't it 1 and 1? To answer that, look at the graph of x squared. You know what that graph looks like. And if you're restricting your attention to values between -1 and 1, what is the range? Right? This function takes on all values between 0 and 1. It's the range we're talking about here. Convinced? So what? What have we done? We have gotten rid of the sign. We've gotten rid of the sign. So now we can just talk about this series here. If we can establish the convergence of this series, and I say if because that's not immediately clear, but if we can establish the convergence of this series, then by the comparison test, the smaller series will converge as well. So if the big one converges, then the smaller one converges. What can we say about that series? Haroon likes the comparison test, and nothing wrong with that. Very nice. Very nice. Let's not do that. Let's use the limit comparison test instead. What are we going to use the limit comparison test with? Numerator is k. That's settled. For large values of k, k cubed is the dominant term in the denominator. Right? This 1 is negligible. So this is going to behave like k over k cubed or 1 over k squared. 1 over k squared, which is a convergent p series, where p is equal to 2, bigger than or equal to bigger than 1. And if we do a limit comparison here, one of them divided by the other, this is just k cubed over 1 plus k cubed. Factor out a k cubed from the denominator. These cancel out. As k goes to infinity, this goes to 0. The whole limit is 1. It is important to state that p bigger than 1, so that the marker knows what you're doing, and knows and understands that you have understood everything that's going on. This is part of the justify your work. Right, so here your limit is between 1 and infinity. And again, right, it's important to state that so that the marker knows that you know what's going on. You've got a limit between 0 and infinity. So both converge or both diverge. This one was convergent. So that series converges by the limit comparison. And consequently, from here, the original series converges by comparison. A beautiful, beautiful example. And if k cubed is k squared, how do we handle this? Yes, with a lot of difficulty. With a lot of difficulty. In fact, I'm going to say that we are not equipped in this course to handle that question. If this had been a k squared instead, squared, then we're not doing that. Can you just say P series, P bigger than 1? You should tell me what the P is here, right? I mean, the marker will want to know that you know what P is. Is this a type of question you should expect on the final? Sure, certainly, yeah. I mean, there are more difficult examples, but this is a nice, difficult one. Yeah. I mean, here's the thing, Michael. It's obvious. It's obvious to the marker. The markers are graduate math students. It is obvious to them, but it's not obvious to them that it's obvious to you. That's the problem. And while it might be obvious to Michael, it might not be obvious to somebody else, another student. So, we're putting everybody on equal footing, and we want to know that you know. Shunshan, what are you suggesting here? Instead of sine squared, what instead of sine squared? If this is sine instead of sine squared, if this is sine instead of sine squared, that we are equipped to deal with. Not right now, but next week. Next week we'll be able to deal with that, and we will see that it converges, yes. Ashley is asking, what's the importance of writing this? Well, again, this is to show that you know what's happening. Because in the limit comparison test, you need your limit to be between 0 and infinity. For the limit comparison test, you need your limit to be between 0 and infinity. Here we have 1. Don't stop at 1, right? Just because the limit exists doesn't mean that both behave the same way. Your limit has to be bigger than 0 and less than infinity. And you have to state that so the marker knows what's going on. Of course. Yeah. And And Michael, I mean, it's the same thing, right? When I say you, I mean students, or it's all good. What do we want to do? Why don't we consider this? All right. There we have it. Very nice. Very nice. We will do a limit comparison with the series 1 over n cubed. And what do you know about this series? This is a convergent P series where P is equal to 3, bigger than 1. The obvious question is, why are we comparing this with 1 over n cubed? Well, that's because you're thinking well, as you know, in math, there's never and always, right? So, I mean, if the series is a geometric series and it converges, then yes, you can use that formula. But if it's anything else, then you have to adapt. Back to this, why 1 over n cubed? Well, that's because you're thinking back to Cal 1, and you recall that the limit as theta goes to 0 of sine theta over theta, or sine x over x, as x goes to 0, is is 1. So in this case, absolutely, as n goes to infinity, sine 1 over n over 1 over n, right? I mean, as long as the argument and the denominator go to 0 at the same rate, the limit's going to be 1. So as n goes to infinity, 1 over n goes to 0 at the same rate as this. So that will be 1. And when you cube it, it's still 1. So this is sine cubed 1 over n over 1 over n cubed, and this limit is 1, right, by this argument. What does that mean? Well, this is a limit comparison test, right? One series divided by another. So that limit is 1. 1 is less than 0. It's bigger than 0 and less than infinity. So both converge or both diverge. And this one converges. So that one converges by the limit comparison test. Somebody's suggesting to find what this series converges to for 1 over n squared plus 1. This is another example where we are not really equipped to do that. Right? We can establish the convergence of this series. Right? And this was actually the first example we did today, right? We showed that this converges. We did not show what it converges to. And I think the only easy way to establish what that converges to would be to move to complex variables. Exactly. Would be to move to complex variables. Right? Because you could factor this as n minus I times n plus I, where I is square root of -1, and then split that up as using partial fractions, 1 over n minus I. Yeah, that's not even going to work nicely. Yeah, I don't know. Well, I mean, I suspect something could be done, but the point is, establishing the convergence for this type of question is going to be sufficient here. The book is asking you to find what it converges to. Is that right? What number is that? What page and what number? I'm going to look that up and see what we can do. Give me the page and number. I don't have the book with me, but I'll do it today, and I'll bring it in next time. I strongly suspect, though, so page 716, number 13. No, that's not going to. I don't think that's going to work. This is in the 8th edition, so 11.2. All right, I'll try that, and we'll discuss it on Thursday. Yeah, let's hold off the discussion until Thursday. Do we have time for one more? Let's do one more. Oh yeah, today is Thursday, and Tuesday it is. Thank you, Michael, for pointing that out. We'll see. I mean, if you want to see me during my office hours, I have office hours today from noon to 2. I'll have my book. We can look at that together. Let's do one more, though, before we end. 54. No, 52. If an is bigger than 0 and the series an converges, show that the series ln of 1 plus an also converges. All right. There you have it. If you have a convergent series of positive terms, then the series of lns also converge. We know that an is less than 1 absolutely. Eventually, right? This is going to be less than 1. But that would mean that this term is going to be less than ln 2. Questionable. We don't need, right? I mean, Haroon is suggesting to, well, if we make this less than or equal to 1 plus an, we're going to have a big issue with the 1. No, because the 1 plus an, the 1, you're adding 1 plus 1 plus 1 infinitely many times, and that's going to be a big issue. That's what I expected, Michael. Thank you for that. That's what I expected. And, you know, I mean, it's easy to read too much into these types of questions. So Michael has confirmed what I suspected, in that it's not asking you what it converges to. It's asking you to approximate what it converges to by calculating the first 8 terms in the sequence of partial sums, or S8, if you will. But I mean, Haroon has suggested, right? I mean, maybe. So you know, you start with this idea, because I mean, look, I mean, we're in a comparison test situation. So it makes a lot of sense to ask the question, how is ln of this related to that? That's the question. How are these things related? And let's generalize this, right? Because if this converges, then this goes to 0. So in other words, how is ln of 1 plus x related to x as x goes to 0? That's really the question. That's the question. So let's investigate that. What is the limit as x goes to 0 of ln 1 plus x over x? Well, as x goes to 0, this goes to 0, ln of 1 is 0, so this has the form 0 over 0. What are we going to do? Quick L'Hopital's rule seems appropriate here. Derivative of ln is 1 over times the derivative of the inside. Derivative of the denominator is 1. This limit is 1. So for large value, so for x close to 0, this business is going to be very close to 1, so less than 2. Consequently, for x close to 0, ln of 1 plus x is going to be less, right? Bring the x to the other side. It's going to be less than 2x. In other words, for large n, an is going to be close to 0. So we get ln of 1 plus an is less than or equal to 2an. The series 2an, which is twice the series an, converges. And this is bigger than or equal to 0. This converges, so the smaller one converges by comparison test. A beautiful final exam question. There it is. How are we doing? Questions? So practice this comparison test, limit comparison test. And we'll pick this up again. How do we know for large n it is equivalent to an near 0? Well, your series converges. So by the divergence test, the ANs have to go to 0. Why did we pick 2 on the other side of the inequality? Anything bigger than 1 really would have done the trick. 1.5, 1.1, 1.01, doesn't matter. Anything bigger than 1, right? We're saying that for x very close to 0, your function is going to be very close to 1. So if you pick anything bigger than 1, then you're going to be closer to 1 than whatever that value is. Anything bigger than 1 would have done the trick. As Paul suggests, 2 is there just to have a constant to reference exactly that. All right. Thank you all for coming, folks. You guys have a good weekend. Practice this. We'll pick this up again on Tuesday. You guys have a good one. I'll see you guys then.